In this class, let's solve few problems from the Poisson equation. So the difference between Laplace equation and Poisson equation is, if it is del squared equal to 0, then it is a Laplace equation. If you have some non-zero function, then we call it as Poisson equation. And we also studied the difference equation corresponding to the Poisson equation. That is the scheme. If you take the scheme, if this point, if you want the value at this mesh point, ui comma j, then it depends on the neighboring mesh points, u I minus 1 comma j, u I plus 1 comma j, u I comma j plus 1, because this is the direction of increase for y-axis and this is the direction of increase for x-axis. So this is on the same line perpendicular to x-axis, so the I coordinate is same I, but j has an increment, so it is j plus 1. So below this point will be u I comma j minus 1. So then the difference equation we saw in the last class is u I comma j plus 1, the point above, plus u I plus 1 comma j, the point to the right, plus point below u I comma j minus 1, plus point to the left u I minus 1 comma j minus 4 times uij. This is the difference equation corresponding to the partial differential coefficient del squared u. Del squared u, when you rewrite in terms of difference coefficient, we get this expression. And in the question, we are given by, it will be by h square, carrying the h square to the right hand side, it will be h squared into f of x comma y. That is because we both x and y have the equal increments. It is x is ih and y is jh. So this is the differential equation corresponding to the Poisson equation. And now let's construct the mesh as per the given problem, and let's find the mesh points, value of the mesh points. So we are given x varies from 0 to 3, y varies from 0 to 3, and we are given the mesh length is 1 unit. So let's start constructing the mesh. This is y equal to 0, y is equal to 1, y is equal to 2, and finally y is equal to 3. This is the direction for increment of y value, and this line y-axis is our x is equal to 0, so x is equal to 1, x is equal to 2, and x is equal to 3. So this is the incremental value for x direction. So this is our x-axis. This is 0, x equal to 1, x equal to 2, x equal to 3, y equal to 1, y equal to 2, y equal to 3. We are interested in finding the value at these mesh points, u1, u2, u3, and u4. To do this, we are given the boundary conditions, that is u equal to 0 along the boundaries. So u along this mesh points, the value at the mesh points are all mesh points along the boundary are all 0. because that's what given in the question. U is 0 on the boundary. So all these mesh points along the boundary, U equal to 0. Now using this scheme, let's form the linear equations and solve them. We are given from the given expression, we have f of x comma y is equal to minus 10 into x squared plus y squared plus 10. So the value of f of IH comma JH is going to be minus 10 into I squared into H squared plus J squared into H squared plus 10. And we are given the mesh length, that is H is equal to 1 unit. So substituting H is equal to 1, we get minus 10 into I squared plus J squared plus 10. Now let's find the expression at each of the mesh point U1, U2, U3 and U4. Before that, we can also check the symmetry of the function f of x comma y. Since all the boundary conditions are 0, the given mesh is symmetric about all the lines, about this diagonal, and about the line through this. So because all the boundary conditions are 0, it is symmetrical. It has around 6 lines of symmetry. So we are not bothered about the mesh values. But the right hand side is a non-zero function. So we should take into account the symmetric nature of the function f of x comma y. If you take the function f of x comma y, you replace x by minus x, equation remain unchanged. So it is symmetric about the y-axis. If you take, if you replace y by minus y, equation remains unchanged. So it is symmetric about x-axis. But unfortunately, we don't have the mesh extended to outside the first quadrant. So this symmetry will not help us. But if you interchange x with y, the equation remains unchanged. So this line is a line of symmetry. So from this we can say U1 is equal to U4, because even without this idea we can start solving the problem, but it may help us. It will reduce one of the equations. Number of unknowns will be reduced to 3 if you apply the symmetry conditions. So now let's represent the difference equation at the mesh points. So at U1, if you take the point U1, at U1 we can find the neighboring points. That is, first let's give the values for I and j. Here I is equal to 1 and j is equal to 2. And now let's go for the schematic representation. The point above, it is 0 plus point to the right U2, point below U3, point to the left 0 minus 4U1 is equal to minus 10 into I squared, that is 1 squared, plus j squared, that is 2 squared, plus 10. So we have got the equation minus 4U1 plus U2 plus U3 is equal to minus 150. Call it equation 1. Now let's move on to the mesh point U2. So at u2, the value of I, again look from the mesh value of I is 2 and the value of j is also 2. So we have I is equal to 2 and j is equal to 2. And applying the schematic representation, value above u2 0, to the right of u2 0, below u2 it is u4, that is same as u1, because we have seen that by symmetry u1 equal to u4. Even we can retain it as u4, you will get 4 equations, 4 linear equations, you can solve them, plus value to the left, it is also u1 minus 4, the value at the mesh point u2, minus 10 into I squared 2 squared, j squared 2 squared, plus 10. So we have got 2u1 minus 4u2 is equal to minus 180. So on simplifying, we get 2, cancelling 2 throughout, u1 minus 2u2 is equal to minus 90. Call it equation 3. Now let's check the values at the mesh point u3. So at u3, we find I is equal to 1, j is equal to 1. I is equal to 1, j is equal to 1. And the point above u3 is u1. To the right of u1, u3 is u4, which is again u1. Below u3, 0. To the left of u3, 0. And the mesh point, minus 4 times the mesh point, that is u3, is equal to minus 10 into I, that is 1 squared, plus j squared, 1 squared, plus 10. So on simplifying, we get 2u1 minus 4u3. Let's use the same blue color. 2u1 minus 4u3 is equal to minus 120. Cancelling out the common terms, we have u1 minus 2u3 is equal to minus 60. Call it equation 3. So now let's solve these equations 1, 2 and 3 to get the values of u1, u2 and u3. We have 3 unknowns u1, u2, u3. We need not find u4 because it is same as u1. Solving these equations, equation 2 minus equation 3, or equation 3 minus equation 2, we get 2u2 minus 2u3 is equal to 30. This implies u2 minus u3 is equal to 15. Call it equation 4. And we can solve equation 1 and 2. So, or 1 and 3. Equation 1 plus 4 times equation 3. So 4u1 minus 4u1 and plus 4u1 will get cancelled. We get minus 7 this plus u2 and u3 minus 4u3. So minus 3u3 is equal to minus 240 minus 180. So it is minus 420. Name it as equation 5. On subtracting these two equations and simplifying, we get u3 is equal to 67.5. And on substituting the value of u3, we get u2 is equal to 82.5. Substituting u1 and u2 in any of the known equations, we get u1 is equal to 75, but we have already proved u1 is equal to u4. Therefore, u4 is also equal to 75. So these are the values of the mesh points for the given Poisson equation under the given boundary conditions. Hope you are familiar with solving the linear equations. Now let's do one more problem on Poisson equation. We are asked to solve del squared u is equal to 8x squared y squared for the square mesh given u is equal to 0. Given u is equal to 0 on the 4 boundaries. So on all the boundaries, the temperature u is equal to 0. Now we have to divide the square mesh into 16. Dividing the square mesh into 16 subsquares. Of length 1 unit. So we need a subsquare. We need 16 squares. So it's going to be a 4 by 4 matrix or 4 by 4 column. 0, 1, 2, 3, 4. These along the y-axis. Y is equal to 0, 1, 2, 3, 4. Now the x values. x1, 2, 3, and 4. This along the x-axis. And now we are given, and before naming, let's simplify this problem by taking the center point as origin. Let us consider this to be our x-axis. And this line to be our y-axis. Without loss of generality, we have just moved the square mesh so that the center mesh point will be a lie at the origin. So we are interested to find these mesh points u1, u2, u3, u4, u5, u6, U7, U8 and U9. So we can assume at this point I equal to 0, here I equal to 1, I equal to 2, I equal to -1, I equal to -2. Similarly, the y values, the j, here j equal to 0, j equal to 1, j equal to 2, j equal to -1, j equal to -2. This is the direction of I and this is the direction of j. We have made this because this function, if you look into, it is symmetric about x-axis. Because when you replace y by -y, the function does not change. So this is a line of symmetry. And when you replace x by y by -y, then also function remain unchanged. So it is symmetric about x-axis. When you replace x by -x, the function remains unchanged. So it is symmetric about y-axis. Also, if you interchange x and y, the function remain unchanged. So it is symmetric about the line y equal to x. It is also symmetric about the line y equal to -x. This will lead to, because it is symmetric about the x-axis, if you fold the mesh, these mesh points will coincide. So we have u1 is equal to u7, u2 is equal to u8 and u3 is equal to u9. If you fold along the y-axis, then we find u1 is equal to u3, u4 is equal to u6 and u7 is equal to u9. If we fold along the line y equal to x, we get u1 is equal to u8 and u4 is equal to u8 and u2 is equal to u6. And if you fold along the line y equal to -x, we get u9, u1 is equal to u9, u2 is equal to u6 and u4 equal to u8, which we have already taken. So from this we get, consolidating all these results, we get u1 is equal to u3 is equal to u7 is equal to u9, because u1 equal to u7, u3, u9 and u1 equal to u8. It's by mistake. It is not the case. It is u4 equal to u8 and u2 is equal to u6. It's again u1 equal to u9. Also, equating the other, consolidating the other terms, we get u2 is equal to u4 is equal to u6 is equal to u8. So 4 of these values are equal to each other. So u1, u3, u7, u9 are all equal, and u2, u4, u6, u8 are all equal. Therefore, now our unknowns are reduced to 3, u1, u2 and u5. So we are interested only in finding 3 unknowns. So now let's get the mesh values at these points. So at x is equal to, or at u1, let's frame the equation. at the unknown mesh values are known, the values we need to find, that is u1, u2, u5. Other mesh values you can easily get from that. At u1, we can find I equal to minus 1 and j equal to 1. I is equal to minus 1 and j equal to 1. And value above u1 is 0 because along the boundaries it is 0, plus u2 to the right. Below it is u4, which is same as u2. To the left it is 1 minus, we are at the mesh point u1, so minus 4 u1 is equal to 8 into I squared into j squared. So we get the equation 2u2 minus 4u1 is equal to 8. From this we get minus 2u1 plus u2 is equal to 4. Call it equation 1. Next, let's do at the mesh point 2 at u2. Our u2 lies on the y-axis. So I equal to 0, j equal to 1. We have I equal to 0 and j equal to 1. Value above u2 is the boundary point, and we know the boundary u is 0 along the boundary. To the right we have u3. u3 which is same as u1. Below u2 it is u5. u5, it is unknown quantity, so retain it, u5. Value to the left, it is u1 minus 4 times at the mesh point, that is u2, is equal to 8 into 0 squared into 1 squared, because I is 0 and j is 1 at u2. So on simplifying this, we have 2u1 minus 4u2 plus u5 is equal to 0. Call it equation 2. Now let's solve this at the mesh point u3. So at u3, I hope u3 is the mesh point at the origin. No. Oh, we need not find u3 because u3 is same as u1. So we have to find u5. The value at u5. At u5, we find I is equal to 0 and j is equal to 0. I equal to 0 and j equal to 0. Hope you could visualize the mesh point u5. So above u5, it will be u2. u2 to the right of u5, it will be u6, which is same as u2. Below u5, it will be u8, which is same as u2. To the left of u5, it is u3, which is same as u1, minus 4 times the value at the mesh point, that is u5, equal to 0. So we have u1 So below it is U8 and above U2. So below also it is U8. That is same as U2. And to the left it will be U4, which is again same as U2. So we have 4U2 minus 4U5 equal to 0. On simplifying, we get U2 is equal to U5. Call it equation 3. So we have 3 unknowns and 3 linear equations. So we can solve them. So equation 1 and equation 2. So from equations 1 and 2, adding these two equations, we get minus 3U2 minus 3U2 plus U5 is equal to 4. But U2 is equal to U5. So this implies substituting U2 equal to U5, we get U2 is equal to minus 2. And when U2 is equal to minus 2, substituting in equation 1, this implies U1 is equal to minus 3. U2 equal to minus 2, U1 equal to minus 3, or substituting U2 again in U5 is same as U2, so U5 is also minus 2. So we have got the value for all the mesh points. Therefore, the solution is U1 is equal to U3 is equal to U7 is equal to U9, that is equal to minus 3. U2 is equal to U4 is equal to U6 is equal to U8, that is equal to minus 2, and also U5 is same as U2, therefore it is also equal to minus 2. So let's wind up the elliptic equations with this problem. Now let's have an introduction to the parabolic and elliptic equations. In the last class, we have discussed that we have classified the one-dimensional heat equation, that is dou U by dou T plus alpha square dou U by dou T plus alpha square is equal to dou squared U by dou X squared. We know it's a parabolic equation, parabolic equation. Now we are trying to get the schematic representation for this parabolic equation. To solve this parabolic equation numerically, let's find out the corresponding difference equation. For convenience, we take alpha squared equal to 1 by a, and rewriting the equation, we get dou squared u by dou x squared is equal to a into dou u by dou t. Now replacing them with their corresponding difference coefficients, we get a dou u by dou t is u I comma j plus 1 minus u I comma j by k is equal to the second derivative, the difference coefficient corresponding to the second order derivative dou square u by dou x squared is 1 by h squared into u I plus 1 comma j minus 2 into u I comma j plus u I minus 1 comma j. So this, from this we get, and assuming lambda is equal to k by a h squared, and getting the value of u at the next time row j plus 1. If you know all the values in the previous time row j, based on that row we can find the values at the next time row j plus 1. So we rewrite the expression having u I comma j plus 1 to the left and taking all other terms to the right. So we have u I comma j plus 1 is equal to 1 minus 2 lambda into u I comma j plus lambda into u I plus 1 comma j plus u I minus 1 comma j. So in particular, if you take lambda is equal to 1 by 2, the u I comma j term vanishes because that will be 1 by 2 comma 1 by 2, and the formula reduces to the simplest way, that is u I comma j plus 1, that is the next, the value of u at the next time interval is same as the value to the left in the previous time interval and value to the right in the previous time interval. The schematic representation of the Bender-Smith, this we call as Bender-Smith method, is given below. Similar way, the one-dimensional wave equation, that is dou squared u by dou t squared is equal to a squared into dou squared u by dou x squared. It is hyperbolic in nature as we have classified in the first session of this PDE. And the corresponding difference equation is 1 by k squared u I comma j plus 1 minus 2 into u I comma j plus u of I comma j minus 1 plus equal to a square by h squared into. This again, we try to rewrite the expression with the next time row in the left hand side, that is the terms involving j plus 1 to one end and all other terms to the other end. So for convenience, we take the k square by h squared as lambda squared. So on collecting the terms, we have, as said, discussed earlier, we have taken the value of u at the next time row to the left hand side and the value of u in the previous time rows to the right hand side. So we can find in the right hand side we have the j and j minus 1 terms, but to the left we have j plus 1 terms. J plus 1 term. So and the schematic representation, in particular, with the simplified equation called as explicit formula we can have when the lambda square a square value is 1. So that if you can choose such a way that choose your lambda so that lambda square a square is equal to 1, then we can use the simplified formula, and the corresponding schematic representation for the solving the hyperbolic equation is below. Now let's solve problems based on the elliptic and the parabolic and the hyperbolic equation. First, let us solve the equation corresponding to the one-dimension heat equation. So the first problem in the parabolic equation, solve uxx is equal to ut given the boundary conditions u of 0 comma t equal to 0, u of 4 comma t equal to 0, u of x comma 0 is equal to x into 4 minus x. These are the boundary conditions given, and we are asked to take h is equal to 1 and k is equal to 1, and we are asked to find the values of u up to t equal to 5 at first 5 time spaces, up to t equal to 5. So we know the recurrence relation for a Poisson equation, sorry, for the parabolic equation, in particular to the one dimension heat equation, is u I comma j plus 1 is equal to 1 minus 2 lambda into u I comma j plus lambda into u I minus 1 comma j plus u I plus 1 comma j. So where lambda is equal to k by a square into h squared. Here all the values are equal to 1. So we have lambda equal to 1 because our a is also 1, that is coefficient of dou u by dou t. So lambda is equal to 1. So on substituting lambda equal to 1 here, we get u I comma j plus 1 is equal to u I minus 1 comma j, because lambda is 1. Giving lambda equal to 1 here, we get minus 1 minus u I comma j plus u I plus 1 comma j. So the schematic representation is, if this is the point u I comma j, and this will be u I plus 1 comma j, and this mesh value will be u I minus 1 comma j, and this point will be u I comma j plus 1. So if you need u I comma j plus 1, it is u I minus 1 comma j, that is we have to add this, minus u I comma j plus u I plus 1 comma j. So now let's construct represent this with the help of a matrix. From the given boundary condition, we see x varies from 0 to 4, and we are asked to find the time space up to 4, up to t is equal to 5. So we have the first box. This box corresponds to t equal to 0. This is t equal to 1, 2, 3, 4, and 5. And x is equal to 0, 1, 2, 3, and 4. And finally we take a box, have a box to represent the x and y values. So for convenience, let's take the values here, I comma j. So I is 0, 1, 2, 3. Oh, let's take it the other way. Let this be j, the time space. And let this be I. 0, 1, 2, 3, 4. And we need for 5 time space. So let this be 5. And the I values 0, 1, 2, 3 and 4. Now let's check with the boundary conditions. We fill up the boundary conditions first. When x is equal to 0, we have u equal to 0. That is x is equal to 0. That is the I values. This is the direction for x and this is the direction for t. For convenience, we have taken this way. We can also take the usual x and y axis for this case. So when x is equal to 0, u is 0. So this is the column where x is equal to 0. So all these values are going to be 0. Now let's check the next boundary condition. When x is equal to 4, u is equal to 0. So when x is 4, u is 0. This is the column corresponding to x is equal to 4. So for all t values, whatever be the t, when x is 4, it is 0. And the last boundary condition, when t is 0, u is x into 4 minus x. So this is the row corresponding to t equal to 0. And at this point, u is equal to x into 4 minus x. So if you take the first row, here x value is 0. Substituting x is equal to 0 here, it is 0. Give x is equal to 1. So 1 into 4 minus 1, 3. Next give x is equal to 2. 2 into 4 minus 2, 4. Next give x is equal to 3. 3 into 4 minus 3, that is 3. Now the next time row, that is j plus 1th row, depend on the jth row by this schematic representation. We have to take the value to the left plus value to the right minus value on the top. So if you need this point, take the value to the left 0, value to the right 4, add them up, subtracting the value above. So it is 4 minus 3, 1. Similarly, if you want to get this row, value to the left plus value to the right minus value above, that is 2. The same scheme, 4 plus 0 minus 3, it is 1. Similarly, if you want to fill up this row, 0 plus 2 minus 1, it is 1. 1 plus 1 minus 2, 0. 2 plus 0 minus 1, it is 1. 0 plus 0 minus 1. 0 plus 0 minus 1 minus 1. 1 plus 1 minus 0, 2. 0 plus 0 minus 1 minus 1. And then 0 plus 2 plus 1. So it is 3. Minus 1 minus 1 minus 2 minus 4. 2 plus 0 minus of minus 1, 3. And the last row, 0 minus 4. It is minus 4 minus the value above, minus 7. 3 plus 3, 6. 6 minus of minus 4, 10. Minus 4 plus 0, minus 4 minus 3. it is minus 7. So we have got all the values corresponding to the 5 time spaces. T is equal to 0, 1, 2, 3, 4 and 5. And this completes the problem. Let's do one more problem in one dimension heat equation, where we can have the choice of our H and T. The question is, solve ut is equal to uxx. So from this we can say A is equal to 3, subject to the boundary conditions are u of 0 comma t equal to 0, u of 1 comma t is also 0, u of x comma 0 equal to sin pi x for 0 less than x less than 1. So we have not given the values for incremental values for x and y, so they are of our choice. So let h is equal to, here x varies from 0 to 1. So whenever we take the incremental value to be minimum, but also it should be convenient for the calculation, then we get the accuracy will be very high. So let's assume h is equal to 2. Choose k such that 1 minus lambda squared a squared will be equal to 0. So that means our k by, that is choose 1 minus 2 lambda is equal to 0. So this implies we should choose lambda is equal to 1 by 2. But the value of lambda is ka by h squared. So we have to choose k by a is 1, h squared is 0.04. It should be equal to 1 by 2. This implies our k should be taken as 0.02, so that we can have the simplified formula, the simplified Bender-Smith formula, that is ui comma j plus 1 is equal to 1 by 2 into ui minus 1 comma j plus ui plus 1 comma j. We can also do the problem by choosing any other value for k that does not reduce lambda equal to 1 by 2. It will be same as the previous case. To use the simplified formula of Bender-Smith, we have chosen this formula. So for the time space, we have to go up to 0.1. Let's do up to 0.1. This corresponds to t equal to 0, and the incremental value for time is 0.02. So this will be 0.02, 0.04, 0.06, 0.08 and 0.1. An additional column for the headers. This we leave for the heading, and the x value varies from 0 to 1, and the incremental value for x is 0.2. So 0, 0.2, 0.4, 0.6, 0.8, and then 1. So this will be the incremental value for x, and this for the time t. We take this to be the positive direction. These are all for our convenience. So here j equal to 0, incremental value 0.02, 0.04, 0.06, 0.08, 0.1. And this incremental value along the x is 0. The incremental value is 0.2, 0.4, 0.6, 0.8, and 1.0. Now let's look at the boundary conditions. The boundary conditions, when x is equal to 0, the temperature is 0. So the points x equal to 0. Here is the case of x is equal to 0. So here along this column, u is 0. And the next boundary condition, when x is equal to 1, then also u is 0. So this is the column corresponding to x is equal to 1. So here also the temperature is always 0. For all the t values, it is 0. Next, we are given u of x comma 0 is sin pi x. That is when t equal to 0, u is equal to sine of pi x. Remember, you have to be in the radian mode. The calculator, while computing the value of sine pi x, you should be in the radian mode. So substituting the first x value 0.2, we get sine of 0.2 pi, that is 0.5878. Next 0.4 pi, that is 0.9511. 0.6 pi, it is also 0.9511. 0.8 pi, 0.5878. And when x is equal to 1, we get sine pi, that is 0. Now this schematic representation, if you want u I comma j plus 1, it is the value u I minus 1 comma j plus u I plus 1 comma j. Add these two values and divide by 2. We need not need the value for u I comma j. So this new, the next time space, it is just the value to the left plus value to the right by 2. That is equal to 0.4756. And here again, value to the left plus value to the right by 2. That is 0.7695. Again, value to the left plus value to the right by 2. 0.7695. And repeating the process, we get 0.4756. Similarly, we get the values at the next time space. That is when t equal to 0.4, it works out to be 0.3848. Sum of these two values divided by 2. And sum of these two by 2, 0.6225. And this value is also 0.6225. And this will be 0.3848. And similarly, the next row will be 0.3848. 0.3113 and this row 0.5036 and the next row next point 0.5036 and the next one 0.3113 and by the similar calculation we get the next value to be 0.2518, 0.4074, 0.4074, 0.2518 and the next value 0.2037, 0.3296. Sum of these two values by 2, 0.3296 and sum of these two values by 2, 0.2037. Let's do the last problem, that is in hyperbolic equation. With that, let's wind up the session. We need another 5 minutes. Hope you would put up with me. Also, one more problem in the one-dimensional wave equation. Solve 4uxx is equal to utt with the boundary conditions u of 0 comma t is equal to 0, u of 4 comma t equal to 0 and the initial conditions, that is a t equal to 0. Ut of x comma 0, that is the initial velocity is 0 and the initial displacement is given by x into 4 minus x. You would have done such problem analytically in Fourier series, applications of Fourier series for 4 time steps, that is up to t equal to 4 we need to compute. So from the given question, we find a squared is equal to 4 and h is equal to 1. We choose k such that 1 minus a square lambda squared is equal to 0. That implies k should be k squared is equal to h squared by a squared or k equal to h by a, that is equal to 1 by 2. But we are not given the boundary, instead we are given the first derivative ut of x comma 0 equal to 0. But we know the corresponding difference coefficient is 1 by k into u I comma 1 plus u I comma minus 1 is equal to 0. So we have u I comma minus 1 is equal to minus u I comma 1. And from the explicit relation, we know that u of I comma 1, that is u of I comma j plus 1 is equal to u I minus 1 comma j plus u I plus 1 comma j minus u I comma j minus 1. So in this, if you put j equal to 0, we have u I comma 1 is equal to u I minus 1 comma 0 plus u I plus 1 comma 0 minus u I comma minus 1. Substituting this u I comma minus 1 here, we get u I comma 1 is equal to u I minus 1 comma 0 plus u I plus 1 comma 0 minus of u I comma 1. This will be u I comma 1 minus, because it's a difference. So from this we get u I comma 1 is equal to 1 by 2 into u I minus 1 comma 0 plus u I plus 1 comma 0. And so by giving the various I values, we can find u I comma 1 comma 1 u1 comma 1 is equal to u0 u2 comma 0 plus u0 comma 0 by 2, that is equal to 2. u2 comma 1 is equal to 3. u3 comma 1 is equal to 2 and u4 comma 1 is 0. Now let's construct the rectangle or the matrix. With that, the problem will be over. We need to find for I equal to 4 time steps, and we have taken the incremental value for I to be 0.5. So this is for the heading, then 0.5, 1, 1.5, 2, 2.5, 3, 3.5 and 4. We are asked only up to 4 time steps. And for the x values, heading x0, 1, 2, 3 and 4. So this is j value and this is I value, 0, 0.5, 1.5, 2.0, 2.5, 3.0, 3.5 and 4. And the x values 0, 1, 2, 3, 4. Just apply the boundary conditions. When x is equal to 0, it is 0. So it's 0, 0, 0, 0, 0, 0, 0, 0. And when x is equal to 4, then also it is 0. So 0, 0, 0, 0, 0, 0, 0. When t equal to 0, u is equal to x into 4 minus x. So substituting x equal to 0 here, we get 0. Then substituting x is equal to 1, 3. X is equal to 2, 4. X is equal to 3, it is 3. And from the schematic representation and from this formula, u I 1 comma 1, u 1 comma 1 is 2, u 2 comma 1, that is the next I value, it is 3, u 3 comma 1 is 2 and is 0. And from the schematic representation, it is going to be sum of these two minus this value. So 3, 0 plus 3 minus 3, 0. 2 plus 2, 4 minus 4, 0. 3 plus 0 minus 3, 4. And repeating the values, the same steps in the other cases, we get minus 2, minus 3, minus 2, then minus 3, minus 3, minus 4, minus 3, and minus 2, minus 3, minus 2, and 0, 0, 0, 2, 3, 2. So with this completes the solution at the various points. Hope you would have enjoyed the session. Thank you. Hello, sir. Yes, sir, it's